Tonight, I want to invite you to step outside your everyday sense of scale and look at something so familiar that we almost never question it: the size of Earth. We live our entire lives on this planet. We walk its continents, cross its oceans, and build our stories upon its surface. From where we stand, Earth feels vast, solid, and permanent. It feels like the stage on which everything that matters unfolds. But what if that feeling is an illusion created by perspective? What if Earth is not just small, but so small that when placed in its true cosmic context, it nearly vanishes altogether? This is not a comparison between Earth and a mountain, or Earth and the sun. This is a journey toward the deepest scale we know, the scale where familiar reference points break down and intuition begins to fail. As we move outward, step by step, Earth will slowly lose its dominance, its centrality, and eventually even its visibility. Along the way, we are not chasing equations or technical detail. We are chasing understanding, the kind that quietly reshapes how you see yourself, your problems, and your place in existence. By the end of this journey, Earth will still be home, but it may no longer feel as large, as central, or as guaranteed as it once did. That realization can feel unsettling at first, but it can also be strangely comforting. There is something powerful about understanding where you truly stand in the grand structure of reality. If you enjoy explorations like this, journeys that trade noise for perspective and speed for depth, taking a moment to like this video or subscribe genuinely helps this channel continue creating them. Now, take a breath. Let the scale of things loosen its grip on your assumptions, and let's begin with a simple question that turns out to be anything but simple. How small is Earth? Really? Before Earth becomes small, before it begins to shrink under the weight of cosmic comparison, we have to acknowledge something important. From a human perspective, Earth is enormous. It feels endless. You can spend a lifetime moving across its surface and still only see a fraction of what it contains. Continents stretch for thousands of miles, broken by mountain ranges that rise so high they pierce the sky, and oceans so deep they hide entire worlds beneath their surface. More than 70% of the planet is covered by water, vast rolling expanses that once took months or even years to cross. Even today, flying from one side of the planet to the other can take more than half a day, passing over deserts, forests, ice caps, and cities without ever leaving the same world. From this viewpoint, Earth doesn't feel small at all. It feels overwhelmingly large. For early humans, it felt infinite. When you stand on the ground and look toward the horizon, the land appears flat, stretching outward without visible curvature. The sky arches overhead like a dome, the sun and stars moving across it in predictable paths. With no way to see beyond that horizon, it was natural to believe the ground went on forever, and that Earth itself was the entire universe. That belief wasn't ignorance. It was the most reasonable conclusion based on direct experience. Even today, the curvature of Earth is so subtle that you can't perceive it without rising far above the surface. Quantitatively, Earth is impressive by any human standard. Its diameter is about 7,900 miles, and its total surface area is roughly 197 million square miles. To put that into something you can feel, imagine attempting to walk around Earth's equator. If you could somehow walk on water and maintained a steady pace of 3 miles per hour, walking 8 hours a day, it would take you just over 3 years to complete the journey. That's a single loop around the planet, without detours, without stopping to explore, without climbing a mountain or crossing a desert. And if you tried to visit every square mile of Earth, spending just 1 second in each location, it would take more than 6 years of continuous movement, without rest. These numbers matter because they explain why Earth feels so large to us. Our bodies, our lifespans, and our experiences evolved at this scale. Earth is the reference frame against which everything else is measured. And that's exactly why what comes next is so disorienting. Because once we step beyond this familiar perspective, once we stop measuring Earth against human limits and begin measuring it against the universe itself, that sense of vastness begins to dissolve. Once we leave the surface of Earth, the first shift in perspective happens almost immediately, and it comes from the most familiar object in our sky. The moon feels close. It rises every night, hangs above us like a companion, and for most of human history, it felt almost within reach. It marks time, guides tides, and lights the darkness. Because it appears so prominent in the sky, many people instinctively imagine it as nearby, almost attached to Earth. But the moment we begin to measure the Earth-Moon system, something strange happens. The scale no longer behaves the way intuition expects. The moon is smaller than Earth, but not dramatically so. Its diameter is about 2,100 miles, roughly 27% of Earth's diameter. If Earth were the size of a basketball, the moon would be closer to a tennis ball than a grain of sand. This already challenges the idea that moons are tiny companions, because most moons in the solar system are minuscule compared to their planets. Ours is unusually large. In fact, the Earth-Moon system is sometimes described as a double planet because of how significant the moon is relative to Earth. But the real revelation doesn't come from size. It comes from distance. The moon orbits Earth at an average distance of about 239,000 miles. That number is hard to feel, so translate it into something grounded. It's roughly the same as driving around Earth's equator 9.5 times. Even at highway speeds, it would take days of non-stop travel. In space terms, that distance is small. In human terms, it's immense. And here's where the illusion breaks. The distance between Earth and the moon is about 30 times Earth's diameter. You could line up 30 Earths side by side in the empty space between the two. Nothing fills that gap. No hidden clouds, no dense medium. Just vacuum. Most images you've seen of Earth and the moon together are deeply misleading. They're often shown large, close, and dramatic, framed together for visual impact. In reality, if you scaled them accurately, they would look lonely, separated by an unsettling amount of emptiness. This is the first time we encounter a fundamental truth about the universe. Space is not full. It is mostly nothing. Even in our immediate cosmic neighborhood, distances vastly outweigh objects. The moon's presence still matters deeply. Its gravity pulls on Earth's oceans, creating the tides that shape coastlines and ecosystems. It also stabilizes Earth's axial tilt. Without the moon, Earth's rotation axis could wobble chaotically over millions of years, triggering extreme climate swings that might make complex life difficult or impossible. The moon has quietly protected Earth's long-term stability. There is also a remarkable coincidence written into this system. The moon appears almost exactly the same size in the sky as the sun. This is not because they are similar objects. The sun is about 400 times larger than the moon, but it is also about 400 times farther away. That accidental balance allows total solar eclipses, moments when the moon perfectly covers the sun, briefly revealing the sun's outer atmosphere. This alignment is temporary. The moon is slowly drifting away from Earth, moving about 1.5 inches farther each year. Billions of years ago, it was much closer. Days on Earth were shorter, tides were stronger, and the sky would have looked very different. Over deep time, this quiet separation continues. And with that realization, something subtle but important settles in. Even the nearest object beyond Earth reveals that the universe is built less from things than from the spaces between them. Once the scale of emptiness reveals itself between Earth and the Moon, the next step outward delivers a far deeper shock to intuition. The sun feels familiar in a different way. It warms the skin, sets the rhythm of day and night, and defines the seasons that shape every ecosystem on Earth. For most of human history, that steady presence made the sun feel supportive rather than overwhelming. But when we place Earth beside the sun in true proportion, the illusion of balance collapses. The sun's diameter is about 864,000 miles, roughly 109 times wider than Earth. That alone is difficult to visualize, but diameter barely hints at the real difference. Volume is where the comparison becomes humbling. You could fit about 1.3 million Earth-sized planets inside the sun, and they would still not fill it completely. Every ocean, every continent, every city, every living thing that has ever existed on Earth occupies less than 1/1,000,000th of the sun's interior. And even that understates the sun's dominance, because size is only part of the story. The sun contains 99.86% of all the mass in the entire solar system. Everything else combined, all the planets, moons, asteroids, comets, and dust, make up a fraction of a single percent. Earth is not a co-star in this system. It is a minor component orbiting a central powerhouse. The distance between Earth and the sun reinforces this imbalance. On average, Earth sits about 93 million miles away. This distance is so fundamental that astronomers use it as a unit of measurement, calling it 1 astronomical unit. Light, the fastest thing in the universe, takes a little over 8 minutes to cross that gap. That means when you see sunlight, you're not seeing the sun as it is now, but as it was more than 8 minutes ago. If the sun were to vanish instantly, Earth would continue orbiting, bathed in warmth and light, completely unaware for those final 8 minutes. Even this vast distance does not make Earth safe from the sun's influence. At its core, the sun is a nuclear furnace, fusing about 600 million tons of hydrogen into helium every second. That process releases an unimaginable amount of energy. In a single second, the sun produces more energy than all of human civilization has generated in its entire history. This constant fusion creates outward pressure that balances the crushing gravity trying to collapse the sun inward. It is a delicate equilibrium maintained over billions of years. Yet the sun is not perfectly calm. It releases enormous bursts of energy in the form of solar flares and coronal mass ejections. When these eruptions are directed toward Earth, they can light the polar skies with auroras, but they can also disrupt satellites, power grids, and communication systems. Earth's magnetic field shields us from the worst of this radiation, but the vulnerability remains. Our planet survives not because it is powerful, but because it occupies a narrow, fortunate position within the sun's reach. This realization forced one of the most profound shifts in human understanding. For thousands of years, people believed Earth sat at the center of everything, with the sun and stars revolving around it. This geocentric view matched everyday experience and reinforced a sense of cosmic importance. But careful observation revealed cracks in that picture. Thinkers like Copernicus proposed that Earth was not the center at all, but just another planet orbiting the sun. Galileo's observations confirmed it. Earth was demoted from the throne. The sun did not circle us. We circled it. This was humanity's first true lesson in cosmic humility. The Sun did not exist for Earth. Earth existed because of the Sun. And with that shift, the idea that Earth might be small, not just physically, but in significance, began to take hold. Once Earth is no longer the center of the solar system, once it is clearly a planet orbiting a star rather than the anchor of everything else, the next question becomes unavoidable. What kind of planet is Earth, really, when compared to its neighbors? If size alone determined importance, Earth would already be unimpressive. But habitability is not about size. It is about conditions. And when we examine the inner solar system closely, Earth's story begins to look less like dominance and more like luck balanced on a narrow edge. Closest to the Sun is Mercury, a world that shows what happens when proximity replaces balance. Mercury is small, dense, and almost airless. Its diameter is only about 38% of Earth's, and with virtually no atmosphere to trap heat or distribute energy, its surface experiences some of the most extreme temperature swings in the solar system. Under direct sunlight, temperatures can soar to around 800 degrees Fahrenheit. Just a short distance away, in permanent darkness, temperatures plunge to nearly minus 290 degrees. Day and night on Mercury are not gentle cycles. They are violent transitions. A single day on Mercury, measured from one sunrise to the next, lasts 176 Earth days. This is because Mercury rotates very slowly while orbiting the Sun relatively quickly. In fact, a Mercury day is longer than a Mercury year. Time itself behaves differently there. Any environment exposed to these conditions would be relentlessly hostile to life as we know it. Mercury shows us that being close to a star is not an advantage. It is a liability. Moving outward, we reach Venus, a planet often described as Earth's twin because of its similar size and composition. At first glance, Venus seems promising. Its diameter is about 95% that of Earth, and its mass is comparable. But the similarities end there. Venus is a warning written in planetary form. Its atmosphere is thick, crushing, and composed mostly of carbon dioxide, with clouds of sulfuric acid drifting through its skies. The surface pressure is about 90 times that of Earth, equivalent to standing nearly 3,000 feet underwater. Temperatures on Venus hover around 900 degrees Fahrenheit, hot enough to melt lead, and they remain nearly constant across the entire planet, day and night, pole to equator. This is the result of a runaway greenhouse effect. Sunlight enters Venus's atmosphere easily, but the heat cannot escape. It becomes trapped, amplified, and locked in place. Venus is actually hotter than Mercury, despite being farther from the Sun. Distance alone does not guarantee safety. Venus rotates slowly and in the opposite direction of most planets, meaning the Sun would rise in the west and set in the east if you stood on its surface. One day on Venus lasts longer than one Venus year. Whatever processes once shaped this world pushed it past a tipping point from which it never recovered. Venus demonstrates that Earth's climate stability is not inevitable. It is fragile. Then comes Earth, placed between two extremes, not scorched like Mercury, not smothered like Venus. Earth orbits at just the right distance for liquid water to exist on its surface. Its atmosphere is thick enough to regulate temperature, but thin enough to avoid trapping catastrophic heat. Its magnetic field deflects harmful solar radiation. Its rotation is fast enough to prevent extreme temperature contrasts. Earth does not dominate this region. It occupies a narrow window where multiple conditions align. Move slightly inward or outward, and the balance collapses. Beyond Earth lies Mars, a planet that once may have looked far more familiar than it does today. Mars is smaller than Earth, about 53% of Earth's diameter, and with weaker gravity, it struggled to hold onto its atmosphere. Evidence carved into its surface tells a clear story. Ancient riverbeds, dried lake basins, and mineral deposits show that liquid water once flowed across Mars. It likely had a thicker atmosphere and a warmer climate billions of years ago. But something changed. Mars lost its magnetic field when its interior cooled and solidified. Without that protective shield, the solar wind gradually stripped away its atmosphere over hundreds of millions of years. As pressure dropped, water could no longer remain liquid on the surface. It either froze or evaporated into space. Today, Mars is a cold desert world with an average surface temperature around -80 degrees Fahrenheit. While equatorial regions can briefly warm above freezing, the thin atmosphere offers little protection. Mars shows that habitability is not permanent. A planet can lose it. Between Mars and Jupiter lies a region that is often misunderstood: the asteroid belt. Popular imagination depicts it as a dense minefield of tumbling rocks where navigation requires constant evasive maneuvers. In reality, the asteroid belt is mostly empty space. Though it contains millions of rocky objects, the distances between them are vast. You could fly through the belt and never see an asteroid with the naked eye. The total mass of all asteroids combined is less than 4% of the Moon's mass. The largest object there, Ceres, is only about 580 miles across. The asteroid belt is not a graveyard of shattered worlds. It is a leftover region where planetary material never coalesced into a full planet, likely disrupted by Jupiter's immense gravity. This region reinforces a recurring theme. Space is not crowded, it is sparse, and structure is the exception, not the rule. Taken together, the inner solar system tells a sobering story. Mercury is too hot and too extreme. Venus crossed a climatic point of no return. Mars lost its protective systems and slowly died. The asteroid belt never became a world at all. Earth sits among these outcomes not as the largest or most powerful planet, but as the most fortunate. Its habitability depends on a precise alignment of factors: distance from the Sun, atmospheric composition, magnetic shielding, internal heat, and geological activity. Remove or alter any one of these, and Earth's story might have resembled its neighbors. Earth's uniqueness here is not a mark of superiority. It is a reminder of how narrow the conditions for life truly are. The inner solar system is not a collection of Earth-like worlds with Earth at the center. It is a gradient of failure modes, with Earth occupying a rare stable zone between them. And this realization quietly prepares us for what comes next. Because if Earth is already small and precarious within its own neighborhood, then stepping beyond the inner solar system will make that fragility even harder to ignore. As we move beyond the fragile balance of the inner solar system, the scale of things changes abruptly. The rocky worlds fade behind us, and we enter a region dominated not by solid ground, but by giants, planets so massive that they reshape the architecture of the entire solar system. The first of these is Jupiter, a world that immediately overwhelms any lingering sense of Earth's importance. Jupiter's diameter is about 86,000 miles, more than 11 times wider than Earth. But width still fails to capture its true dominance. Jupiter's volume is so vast that more than 1,300 Earths could fit inside it, and even then, there would be room left over. Its mass exceeds that of all the other planets combined. If the solar system had a gravitational ruler, Jupiter would be it. Its immense gravity reaches far beyond its visible clouds, influencing the orbits of asteroids and comets throughout the solar system. This gravitational reach has likely played a critical role in Earth's survival. By capturing or deflecting countless objects that might otherwise have plunged into the inner solar system, Jupiter acts as a kind of cosmic shield. It is not a perfect protector, but without Jupiter's presence, Earth may have experienced far more catastrophic impacts, making the emergence of complex life far less likely. Even so, Earth remains insignificant. Beside this giant, a small rocky world orbiting far inside the realm Jupiter quietly governs. Jupiter's moons deepen this perspective shift even further. The four largest, known as the Galilean moons, are not mere satellites, but worlds in their own right. Io is the most volcanically active body in the entire solar system, its surface constantly reshaped by eruptions driven by Jupiter's tidal forces. Europa appears calm and icy on the surface, but beneath its frozen crust lies a global ocean of liquid water, possibly containing more water than all of Earth's oceans combined. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury, complete with its own magnetic field. Callisto, heavily cratered and ancient, preserves a record of the solar system's early history. These moons demonstrate something unsettling. Some of the most promising environments for life may not exist on planets at all, but on moons orbiting giant worlds. Earth is not just small compared to Jupiter. It is not even the only place nearby where conditions suitable for life might exist. Moving farther out, Saturn emerges, nearly as imposing as Jupiter, but visually unforgettable. Its diameter spans more than 72,000 miles, and its volume could contain over 700 Earths. Saturn's most iconic feature, its rings, appear solid and immense from a distance, but they are surprisingly delicate. Composed of countless particles of ice and rock, ranging from tiny grains to boulders the size of houses, the rings extend tens of thousands of miles from the planet, yet are remarkably thin. If Saturn were scaled down to the size of a basketball, its rings would be thinner than a sheet of paper. This contrast between breadth and fragility echoes a recurring theme of the universe, where structures that appear massive are often tenuous when examined closely. Saturn's moons rival Jupiter's in complexity. Titan, the largest, is bigger than Mercury and possesses a thick atmosphere, denser than Earth's. On its surface are lakes and seas, not of water, but of liquid methane and ethane. Hydrocarbon rain falls from the sky, carving river channels and filling basins, creating a chemical cycle that mirrors Earth's water cycle in form, if not substance. Then there is Enceladus, a small icy moon barely 300 miles across, yet one of the most intriguing objects in the solar system. Jets of water vapor and ice erupt from its south pole, feeding a subsurface ocean kept warm by tidal heating. Spacecraft have detected organic molecules within these plumes, the basic ingredients necessary for life. Enceladus shows that even tiny worlds, dwarfed by Earth, can harbor environments that challenge our assumptions about where life might arise. Beyond Saturn, the solar system grows colder and stranger. Uranus stands apart immediately because of its orientation. Its axis of rotation is tilted by about 98 degrees, meaning it effectively rolls around the Sun on its side. As a result, each pole experiences decades of continuous sunlight, followed by decades of darkness. Seasons on Uranus last about 21 Earth years. The reasons for this extreme tilt remain uncertain, but the most likely explanation is a colossal collision early in the planet's history, a reminder that violence on unimaginable scales shaped even the calmest-looking worlds. Uranus is smaller than Jupiter and Saturn, but it still dwarfs Earth. Its volume could contain roughly 63 Earth-sized planets. Neptune lies even farther out, a deep blue world whipped by the fastest winds ever recorded. Wind speeds there exceed 1,200 miles per hour, far faster than anything on Earth. Despite receiving only a fraction of the sunlight Earth does, Neptune is remarkably dynamic, with massive storms that appear and disappear over surprisingly short timescales. One such storm, the Great Dark Spot, was observed by Voyager 2 and later vanished entirely. Neptune completes a single orbit around the Sun every 165 Earth years. Entire human civilizations could rise and fall before Neptune finishes 1 year. And yet Neptune, like Uranus, is still only a planet, one object among many in the Sun's extended domain. Beyond Neptune lies a region that further dissolves Earth's sense of prominence, the Kuiper Belt. This vast disk of icy bodies stretches billions of miles outward and contains remnants left over from the solar system's formation. Here, sunlight is weak, temperatures hover near absolute zero, and objects move slowly along distant orbits. Pluto resides within this region, once considered the 9th planet, and now classified as a dwarf planet. Pluto is only about 1,470 miles across, smaller than Earth's moon. And yet, it is surprisingly complex. It has mountains made of water ice, vast plains of frozen nitrogen, and a thin atmosphere that expands and collapses as it moves closer to and farther from the Sun. Pluto is accompanied by a large moon, Charon, so close in size that they orbit a shared point in space rather than one simply orbiting the other. Pluto is not an exception. It is one of many similar objects in the Kuiper Belt, and likely only the largest we have been able to observe so far. Taken together, the outer solar system delivers a clear message. Earth is not merely small in comparison to stars or galaxies. It is dwarfed even within its own planetary system. Giant planets dominate mass and gravity. Moons rival planets in size and complexity. Habitable environments may exist far from the Sun, hidden beneath ice rather than basking in warmth. Earth is not the centerpiece of this system. It is a modest, rocky world nestled close to its star, overshadowed by giants and surrounded by regions so vast that Earth's orbit occupies only a tiny inner fraction. The further outward we travel, the clearer this becomes. Earth does not grow in importance with distance. It recedes, and as we approach the outer edges of the Sun's influence, even the idea of the solar system as a compact, orderly structure begins to dissolve, setting the stage for an even more dramatic realization about how far the Sun's reach truly extends. As vast as the outer planets and the Kuiper Belt may seem, they still do not mark the true boundary of the solar system. What we have described so far is only the visible core, the region where planets move in relatively flat, orderly paths around the Sun. Beyond Pluto, beyond the last icy bodies of the Kuiper Belt, the structure of the solar system changes completely. Distance stops behaving intuitively, and the Sun's domain stretches outward into something far larger and more diffuse than most people imagine. Far beyond the planets lies the Oort cloud, a vast spherical halo of icy debris surrounding the solar system in all directions. Unlike the Kuiper Belt, which forms a flattened disk, the Oort cloud is more like a cosmic shell, extending tens of thousands of astronomical units from the Sun. Its outer edge may reach nearly 2 light-years away, almost halfway to the nearest star. At this scale, the Sun no longer dominates space with authority. Its gravitational grip is weak, barely holding on to these distant objects. They move slowly, drifting in enormous orbits that can take millions of years to complete. The Oort cloud is so distant that no human-made object has ever come close to it, and no telescope has directly observed its members. We infer its existence because of comets. Long-period comets, the ones that appear suddenly from seemingly random directions, are visitors from this remote realm. A passing star or a subtle galactic tide can disturb an Oort cloud object, nudging it inward. Over thousands or millions of years, it falls toward the sun, briefly lighting up our skies before returning to the cold darkness or being lost forever. These comets are messages from the edge of the sun's influence, reminders of how far the solar system truly extends. When you include the Oort cloud, the solar system is no longer a compact arrangement of planets. It is a structure spanning trillions of miles, a fragile gravitational bubble floating in the vastness between stars. And within that enormous volume, the planets occupy only a tiny inner region, like grains of dust near the center of a cathedral-sized void. From this perspective, Earth is not just small compared to Jupiter or distant worlds like Neptune. It is a microscopic feature deep inside a system that itself is little more than a faint island in an ocean of interstellar space. The solar system, once imagined as the whole universe, is revealed as a thin, fragile outpost, suspended in emptiness, its true scale defined less by what it contains than by how far its influence barely reaches. Once the solar system is understood as a fragile bubble stretching nearly 2 light-years in every direction, a natural question follows. What lies beyond it? The moment we cross that boundary, scale takes another dramatic leap, one that makes even the vastness of the Oort cloud feel small. Beyond the sun's outermost reach begins interstellar space, the realm between stars, where distances are no longer measured in millions or billions of miles, but in light years. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It is about 4.24 light-years away. A light-year is not a unit of time, but of distance. The distance light travels in 1 year, roughly 6 trillion miles. That means Proxima Centauri is more than 25 trillion miles from Earth. To make that distance feel tangible, imagine shrinking the entire solar system so that the distance from Earth to the Sun is just 1 inch. At that scale, Proxima Centauri would be more than 4 miles away. Everything we've discussed so far, the planets, the Kuiper Belt, even the Oort cloud, would fit into a space smaller than a neighborhood, while the nearest star would sit far beyond the horizon. This separation is not unusual. It is the rule. Stars are isolated, separated by vast gulfs of emptiness. Even our closest neighbor is unimaginably far away. The most distant human-made object, Voyager 1, has been traveling since 1977. After more than 4 decades, it has only just crossed into interstellar space, reaching a distance of about 15 billion miles from Earth. At its current speed of around 38,000 miles per hour, Voyager would need more than 70,000 years to reach Proxima Centauri, and it is not even headed in that direction. Even if humanity could build a spacecraft capable of traveling at 10% the speed of light, far beyond anything we can currently achieve, the journey would still take over 40 years. Interstellar distances do not merely slow exploration, they nearly forbid it. Proxima Centauri itself is not an impressive star by human standards. It is a red dwarf, the most common type of star in the galaxy. Red dwarfs are small, cool, and faint compared to stars like our Sun. Proxima Centauri's diameter is only about 14% of the Sun's, and its mass is roughly 12%. It burns its fuel slowly and steadily, meaning it will shine for trillions of years, far longer than the Sun ever will. In fact, no red dwarf star has ever died of old age. The universe simply has not existed long enough. Yet despite its longevity, Proxima Centauri is a harsh environment. It is a flare star, prone to sudden, powerful eruptions that can bathe nearby planets in intense radiation. While it does host at least one known planet in its habitable zone, the region where liquid water could exist, these flares make the long-term survival of life uncertain. Still, the fact that even the nearest star has planets reinforces an unsettling idea. Planetary systems are common. Earth is not orbiting a special kind of star in a special kind of neighborhood. It is one planet among countless others. And yet, from Proxima Centauri, Earth is completely invisible. Even with a powerful telescope, Earth would be lost in the glare of the Sun, too small and too faint to detect. The Sun itself would appear as an ordinary star, indistinguishable from billions of others. Our entire solar system would collapse into a single point of light, and Earth would not register at all. As we look to more distant stars, the effect intensifies. Sirius, the brightest star in Earth's night sky, is about 8.6 light-years away. Betelgeuse, a red supergiant in the constellation Orion, lies roughly 700 light-years from us. The light we see from Betelgeuse tonight left that star when human civilization was still in its infancy. At these distances, Earth does not just vanish physically, it vanishes conceptually. There is no frame of reference in which Earth can be said to exist as a distinct object. Even the solar system becomes insignificant, a tiny spark among countless others. The lesson here is stark. Earth does not retain its importance once we leave the immediate comfort of our own system. Among the nearest stars, among the vast emptiness separating them, Earth is not a destination, not a landmark, not even a speck. It is a hidden detail inside a structure so sparse and immense that isolation becomes the defining feature of the cosmos. Once Earth disappears among even the nearest stars, the next step outward changes the question entirely. We are no longer asking where Earth is. We are asking whether it matters at all within the structure that contains those stars. Every point of light you see in the night sky, every star visible to the naked eye, belongs to a single system, the Milky Way galaxy. What looks like a faint, cloudy band stretching across the sky is not mist or light pollution. It is the combined glow of hundreds of billions of suns packed into a vast rotating structure, and our solar system is embedded deep within it. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across. That means light, traveling at the fastest speed allowed by the universe, takes 100,000 years to cross from one edge to the other. Compared to this, the distance to Proxima Centauri is trivial. If the gap to our nearest star were shrunk to the width of a finger, the Milky Way would stretch for kilometers. Our Sun is just one star among an estimated 100 to 400 billion in this galaxy, and it occupies no privileged position. It sits about 26,000 light-years from the galactic center, tucked into a minor spiral feature called the Orion Spur, a quiet region between two major spiral arms. We are not near the center, not near the edge, and not near anything particularly special. The galaxy itself is structured, but not orderly in the way a solar system is. The spiral arms are regions where gas and dust are compressed, triggering the birth of new stars. These arms glow brightly because they are filled with massive, young blue stars that burn hot and die quickly. Our Sun is not one of them. It is an older, more stable star that has drifted away from the arm where it likely formed. That drift takes time, and time behaves very differently at galactic scales. One complete orbit of the Sun around the center of the Milky Way takes about 225 million years. This is called a galactic year. Since Earth formed, the Sun has completed only about 20 of these orbits. The last time it was in this same region of the galaxy, dinosaurs had not yet appeared. The time before that, the continents were still fused into a single massive landmass. Human history, by comparison, does not even register. Civilizations rise and fall between fractions of a galactic year. Against this backdrop, Earth's entire existence becomes a brief flicker, not just in space, but in time. At the heart of the Milky Way lies a region we cannot see with ordinary light. Dust and gas block our view, but observations in infrared and radio wavelengths reveal what sits there. A supermassive black hole known as Sagittarius X. It contains about 4 million times the mass of the Sun, compressed into a region no larger than our solar system. Stars near the galactic center orbit at tremendous speeds, some completing full orbits in just a few decades. One such star, known as S2, swings around Sagittarius Aces at speeds reaching several percent of the speed of light. This region is chaotic, energetic, and hostile. Earth is far from it, safely distant in a calmer suburb of the galaxy. That distance is not an accident. Regions near the galactic center are bombarded by intense radiation, frequent supernovae, and gravitational disturbances. The relative quiet of our location may be one reason complex life was able to develop here at all. Surrounding the visible disk of the Milky Way is the galactic halo, a roughly spherical region extending far beyond the spiral arms. The halo contains old stars, globular clusters, and something even more mysterious: dark matter. Dark matter does not emit or absorb light, but its gravitational influence shapes the galaxy's rotation. Without it, the Milky Way would fly apart. Most of the galaxy's mass is not in stars or planets, but in this invisible component. Earth, made of ordinary matter, represents an almost negligible fraction of what actually holds the galaxy together. Within the Milky Way are star-forming regions and stellar communities that further erode any sense of planetary significance. Nebulae, vast clouds of gas and dust, stretch for dozens or hundreds of light years. The Orion Nebula, one of the closest star-forming regions to us, lies about 1,300 light-years away and spans more than 20 light-years. Inside it, hundreds of stars are being born right now, their light carving glowing cavities in the surrounding gas. Our Sun formed in a similar nebula over 4.5 billion years ago, alongside countless sibling stars that have since scattered across the galaxy. Some may now be tens of thousands of light-years away, indistinguishable from the rest. There are also star clusters, gravitationally bound groups of stars that form together. Open clusters, like the Pleiades, contain hundreds or thousands of stars and remain together for hundreds of millions of years before dispersing. Globular clusters are even more extreme. They are dense, spherical swarms containing hundreds of thousands or even millions of stars packed into regions only a few hundred light-years across. In the core of such a cluster, the night sky would be filled with thousands of stars as bright as Venus appears from Earth. In these environments, Earth is not small. It is irrelevant. Even entire solar systems are lost in the crowd. When you compress the Milky Way into any kind of scale model, Earth ceases to exist in any meaningful way. If the galaxy were shrunk to the size of a large city, the entire solar system would be smaller than a grain of dust, and Earth would be far smaller still, beyond the limits of visibility or measurement. There is no analogy that preserves its presence. At this level, Earth is not a place. It is a rounding error. The Milky Way is not unique in the universe, but within it, the illusion of importance collapses completely. The Sun is no longer dominant. It is one ordinary star among hundreds of billions. The solar system is no longer vast. It is a microscopic feature embedded in a rotating disk of stars, gas, and dark matter. And Earth, the world that once felt infinite, becomes something even harder to grasp than small. It becomes conceptually negligible, not because it lacks meaning to us, but because the structures that surround it operate on scales so immense that Earth simply does not factor into the equations that govern them. And yet, even this enormous galaxy is not the end of the story. Once the Milky Way itself dissolves Earth into insignificance, the next realization is even more destabilizing. The galaxy that seemed so vast, so dominant, is not alone. It does not exist in isolation, drifting through space as a solitary island of stars. It is part of a larger structure, one that immediately strips away the idea that a single galaxy could ever be cosmically important. The Milky Way belongs to a small collection of galaxies known as the Local Group. This group contains roughly 50 galaxies bound together by gravity, most of them dwarf galaxies with only a few million or billion stars. Two members dominate the group: the Milky Way and Andromeda. Andromeda is larger than our galaxy, containing around 1 trillion stars, more than twice the Milky Way's population. It lies about 2.5 million light-years away, close enough that its faint glow is visible to the naked eye under dark skies. Despite this distance, the Milky Way and Andromeda are not drifting apart. They are moving toward each other. In about 4.5 billion years, the two galaxies will collide and merge, forming a single massive elliptical galaxy. This collision will not resemble anything like a crash in human terms. Stars are so far apart that direct collisions between them will be rare. Instead, the galaxies will pass through one another, their shapes distorted by gravity, their orbits rearranged, their identities erased. By the time this happens, Earth will likely no longer exist as a living world, and the Sun itself may be nearing the end of its life. Even at the scale of the Local Group, Earth has already vanished completely. But the Local Group itself is not a major structure. It is merely a small neighborhood within a much larger environment. Step back again, and the Local Group is revealed as one minor component of a far greater assembly known as the Virgo supercluster. This structure spans roughly 110 million light-years and contains thousands of galaxy groups and clusters. At its heart lies the Virgo cluster, a massive concentration of galaxies located about 54 million light-years away. The Virgo cluster alone contains over 1,000 galaxies, some of them far larger and more massive than the Milky Way. Here, galaxies are packed much more densely than in our quiet corner of space, interacting, merging, and evolving under intense gravitational influence. Within such clusters, the Milky Way is not special. It is not even large. It is one spiral among many, orbiting the gravitational center of a structure so immense that its scale defies any intuitive comparison. If the Milky Way were reduced to the size of a coin, the Virgo supercluster would span the area of a large city. Everything we have discussed so far, the solar system, the Sun, Earth, all of it, would fit comfortably within that single coin. And Earth itself would not be a visible feature even under a microscope. For decades, astronomers believed the Virgo supercluster was the largest coherent structure in our cosmic neighborhood. But that belief did not survive closer examination. In 2014, researchers analyzing the motion of galaxies discovered that the Virgo supercluster was itself only a part of something vastly larger. This newly identified structure was named Laniakea, a word meaning immeasurable heaven. Laniakea is not simply a bigger cluster, it is a supercluster of superclusters, a gravitational basin spanning approximately 520 million light-years and containing around 100,000 galaxies. All of these galaxies, including the Milky Way, are flowing toward a common region of space, pulled by gravity into a vast cosmic current. Laniakea redefines what it means to belong to a structure. It is not a neatly bounded object. It is a gravitational landscape, defined by motion rather than shape. Galaxies within it are not orbiting a single center like planets around a star. They are drifting along immense trajectories, guided by the combined mass of countless galaxy clusters. At the heart of this flow lies a region known as the Great Attractor. This is not a single object, but a dense concentration of mass exerting a powerful gravitational pull. From Earth's perspective, it lies behind the plane of the Milky Way, hidden by dust and gas, which long prevented astronomers from observing it directly. Its presence was inferred through its effects. Galaxies across vast regions of space are moving toward it, their velocities deviating from the smooth expansion of the universe. The Great Attractor revealed a humbling truth. Even at scales of hundreds of millions of light-years, gravity still organizes matter into structures, and our entire galactic neighborhood is being pulled along like debris in a slow-moving cosmic tide. But even Laniakea is not the final word. Observations suggest that beyond it lies an even more massive structure, one whose gravitational influence extends across an even greater volume of space. This is the Shapley supercluster, located roughly 650 million light-years away. It contains thousands of galaxies and is one of the most massive concentrations of matter in the nearby universe. The combined gravity of the Shapley supercluster appears to be pulling Laniakea itself, along with everything inside it, toward its center. At this scale, the idea of a cosmic hierarchy becomes unavoidable. The Milky Way is part of the local group. The local group is part of a cluster environment within the Virgo supercluster. The Virgo supercluster is embedded within Laniakea, and Laniakea is being influenced by structures even larger still. Each step outward erases another layer of perceived importance. There is no final center, no privileged location, no place where Earth, or even the Milky Way, could plausibly claim relevance. These structures do not exist for planets, stars, or even galaxies. They exist because gravity, acting over immense distances and unimaginable spans of time, shapes matter into patterns far beyond anything our senses evolved to comprehend. At this level, Earth is not just small, it is absent. The scales involved are so extreme that even galaxies become interchangeable units, mere points in a flowing cosmic map. The universe no longer looks like a collection of objects. It looks like a vast system of motion, a web of gravity stretching across hundreds of millions of light-years. And this is still not the largest structure the universe has to offer. Once even superclusters lose their sense of finality, the universe reveals its largest recognizable pattern. Galaxies and clusters are not scattered randomly through space, nor are they arranged as isolated islands drifting independently. When astronomers map the positions of millions of galaxies across vast distances, a striking structure emerges. Matter traces immense filaments and walls that stretch across hundreds of millions of light-years, intersecting like threads in a three-dimensional web. This is known as the cosmic web. Along these filaments, galaxies cluster together, flowing along gravitational pathways shaped by dark matter. Where filaments intersect, Galaxy clusters form, dense knots of mass embedded within the larger structure. These regions glow with stars, gas, and energetic processes, while the filaments connecting them appear as faint bridges of matter spanning enormous voids. The walls are thinner, but even more dramatic. Vast sheets of galaxies that form the boundaries between regions of emptiness. These structures are the largest coherent patterns we can observe in the universe, and they define how matter is distributed on the grandest scales. But what is most revealing about the cosmic web is not the matter itself. It is the emptiness between it. The filaments and walls occupy only a small fraction of the universe's volume. The vast majority of space exists in enormous voids, regions where galaxies are rare or nearly absent. These voids can span tens or even hundreds of millions of light-years across. Inside them, matter is so sparse that a lone galaxy may be separated from its nearest neighbor by immense distances. From within a void, the universe would appear eerily empty, with only distant walls of light marking the edges of existence. These voids are not errors or gaps. They are an essential part of the universe's structure. They formed because gravity amplified tiny variations in the early universe. Slightly denser regions pulled matter inward over billions of years, becoming filaments and clusters, while slightly emptier regions lost matter and expanded into vast cosmic cavities. The result is a universe where structure and emptiness coexist, where everything that exists is concentrated into thin threads surrounded by overwhelming nothingness. Our own galaxy resides within one of these filaments, a faint strand of matter embedded in the cosmic web. The Milky Way is not near the center of the universe, because the universe has no center in this sense. It is not located near a special node or an exceptional region. It simply follows the filament it inhabits, drifting along with countless other galaxies toward regions of greater gravitational pull. Earth, by extension, occupies a position so deeply buried within this hierarchy that its location cannot be meaningfully defined beyond saying that it exists somewhere along a minor filament in an unremarkable part of the web. At this scale, Earth does not merely vanish visually or physically. It vanishes conceptually. The universe no longer feels like a collection of objects that could, even in principle, be listed or counted. It becomes a balance between presence and absence, between delicate strands of matter and immense volumes of emptiness. The structures we focus on exist only because they are exceptions. Most of the universe is not filled with stars, planets, or galaxies. It is filled with nothing. And yet, it is this emptiness that gives shape to everything else. The cosmic web is not a dense framework holding the universe together. It is a sparse scaffold suspended in vast voids, a reminder that the universe is defined as much by what is missing as by what is there. And somewhere within one of those thin filaments, orbiting one ordinary star in one ordinary galaxy, lies a planet so small that its presence cannot be marked on any map of this scale. Once the universe is understood as a web of filaments suspended in immense voids, there is only one step left to take, and it is the most disorienting of all. Everything we have described so far, galaxies, clusters, superclusters, filaments, exists within a boundary defined not by matter, but by time and light. This boundary is known as the observable universe. It is not the entire universe. It is simply the portion of it that we can, in principle, see. The reason for this limit is straightforward but profound. The universe has a finite age, about 13.8 billion years. Light travels at a finite speed. Any light emitted from beyond a certain distance has not yet had enough time to reach us. That distance defines our observable horizon. At first glance, you might assume this horizon lies 13.8 billion light-years away. But the universe has been expanding the entire time that light has been traveling. Space itself has been stretching. As a result, the observable universe is far larger than its age in light-years. Today, its diameter is about 93 billion light-years. That is the maximum span of space from which light has reached us since the beginning of cosmic expansion. Everything we can ever observe, no matter how advanced our technology becomes, is contained within that enormous sphere. Inside this observable universe, astronomers estimate there are roughly 2 trillion galaxies. Each galaxy contains anywhere from millions to trillions of stars. The total number of stars is estimated to be on the order of 200 billion trillion. Numbers like these no longer describe quantity in any intuitive sense. They dissolve meaning. At this scale, Earth is not just small, it is mathematically irrelevant. Even the Milky Way, which once seemed impossibly vast, becomes one faint structure among trillions. If you were to select a random star within the observable universe, the odds of selecting the Sun would be so small that they approach zero. And even if you somehow did, the chance of selecting Earth among the countless planets, moons, and debris surrounding it would be smaller still. In any practical sense, Earth does not exist at this level of comparison. But even this overwhelming scale is not necessarily the end. The observable universe is not the same as the entire universe. It is only the region we can see, limited by the speed of light and the age of cosmic expansion. Beyond it, there may be vastly more space, filled with galaxies forever beyond our reach. The universe could be several times larger than what we observe. It could be thousands of times larger. Or it could be infinite. If the universe is infinite, then the observable universe, despite its 93 billion light-year diameter, represents essentially nothing. 0% of infinity. In such a universe, every physically possible configuration of matter would occur not once, but infinitely many times. There could be regions identical to ours, galaxies like the Milky Way, planets like Earth, perhaps even versions of you and this moment, repeated endlessly across space. Some theories in modern physics go even further. Inflationary cosmology suggests that our universe may be one bubble among many, each forming through the same physical processes but evolving independently. Other interpretations of quantum mechanics imply that reality itself may branch, creating countless parallel universes with every possible outcome realized somewhere. These ideas remain speculative. We have no way to observe beyond our cosmic horizon and no direct evidence of other universes. But they arise naturally from well-tested mathematics, and they serve as a final reminder of how provisional our sense of scale really is. Even the observable universe, vast beyond comprehension, may be only a small patch within a reality far larger than anything we can measure. At this point, the breakdown is complete. Earth has not merely shrunk, it has dissolved into abstraction. Against the full scope of what might exist, Earth is not just invisible. It is indistinguishable from nothing at all. After stretching the mind to its limits with cosmic distances and unimaginable expanses, the only way forward is inward. When the universe becomes too large to grasp, perspective flips. Instead of asking how big everything is, we ask what everything is made of. Because scale does not only run outward into galaxies and voids, it also runs inward, down into matter itself. And this descent is just as unsettling. Earth feels solid. Mountains resist. Oceans press. Ground supports our weight. At human scales, matter appears dense, continuous, and substantial. But this impression collapses the moment we cross into the atomic world. Every object, including Earth itself, is built from atoms, and atoms are not solid in the way our senses suggest. An atom is extraordinarily small. The diameter of a hydrogen atom, the simplest and most common atom in the universe, is about 1/10 of a nanometer. That is 1/10 billionth of a meter. You could line up roughly 10 million atoms across the width of a single human hair. Yet even this description hides the deeper truth. An atom is mostly empty space. At its center lies a nucleus, composed of protons and neutrons, surrounded by electrons that occupy a vast region relative to the nucleus itself. If an atom were scaled up to the size of a football stadium, the nucleus would be no larger than a marble at the center of the field. Everything else, the entire volume of the atom, would be empty. The electrons do not orbit like tiny planets. They exist as probability clouds, regions where they are likely to be found, smeared out across space. Matter, at its most fundamental level, is not compact. It is sparse. Earth is made of these atoms, trillions upon trillions of them. Earth's mass is about 6 trillion kilograms, and if you estimate the average mass of the atoms composing it, Earth contains on the order of 10 to the power of 50 atoms. That is a 1 followed by 50 zeros, a number so large that counting it is meaningless. If you counted 1 atom per second, it would take far longer than the age of the universe to finish. But despite this immense number, almost all of Earth's volume is empty space at the atomic level. The solidity we feel is an illusion created by electromagnetic forces. When you stand on the ground, the atoms in your feet are not touching the atoms in the Earth. They are repelling each other through electric forces between electrons. What feels solid is actually force, not contact. This realization allows for a disturbing thought experiment. What if you removed all the empty space from Earth? What if you compressed all its atoms so that the nuclei were touching directly, eliminating the vast gaps between them? Earth would not shrink slightly. It would collapse dramatically. All of Earth's matter, oceans, mountains, core, and crust, compressed to nuclear density, would fit into a sphere only a few hundred meters across. Roughly the size of a large building, a planet 8,000 miles wide, reduced to something that could sit comfortably within a city block. This is not science fiction. It is a direct consequence of how matter is structured. The same is true of everything else in the universe. Stars, planets, even galaxies are mostly empty space. Scale works in both directions. As structures grow larger, they become sparser. As structures grow smaller, emptiness dominates again. Atoms themselves are not fundamental. Protons and neutrons within the nucleus are composed of smaller particles called quarks. 3 quarks bound together form a proton or neutron, held in place by the strong nuclear force, one of the fundamental forces of nature. Quarks are point-like, as far as we can tell. They have no known size. They exist as excitations in underlying quantum fields. Between them is not solid matter, but energy and probability. Even here, emptiness persists. The mass of a proton does not come primarily from the mass of its quarks, but from the energy of their interactions. Mass itself emerges from motion and force, not substance. Below quarks, our understanding ends. They are currently considered fundamental, not made of anything smaller. But history suggests caution. Every time we believed we had reached the smallest building block, we later discovered deeper layers. Atoms gave way to nuclei and electrons. Nuclei gave way to protons and neutrons. Protons and neutrons gave way to quarks. Whether quarks are truly fundamental or not remains unknown. What matters is the pattern. Matter is not a stack of solid pieces. It is a hierarchy of interactions, each layer dominated by emptiness. This creates a strange symmetry with the cosmic scale we just left behind. The universe on its largest scales is mostly void, with matter arranged in thin filaments and scattered clusters. On its smallest scales, matter is mostly empty, with mass concentrated in tiny cores surrounded by vast regions of nothing. The same principle repeats. Structure exists, but it is the exception, not the rule. Earth, when viewed through this lens, occupies a peculiar position. On cosmic scales, it vanishes into insignificance. On atomic scales, it dissolves into emptiness. It is neither large nor dense in any absolute sense. It is a temporary configuration of forces and fields, arranged just long enough for complexity to arise. Even time participates in this inversion. The processes governing atoms unfold in fractions of a second, while cosmic evolution spans billions of years. Human experience sits awkwardly in between, slow compared to particles, fast compared to galaxies. We live in a narrow band where structure feels stable, where objects persist, where cause and effect align with intuition. Step outside that band in either direction, and intuition fails. Compression thought experiments expose this fragility. If Earth were compressed further, beyond nuclear density, it would not remain a planet-sized object. It would become something else entirely. If Earth's mass were compressed into a region smaller than its Schwarzschild radius, it would form a black hole. That radius would be only about 9 millimeters across. The entire planet reduced to something smaller than a marble, not because matter disappears, but because gravity overwhelms all other forces. Size, mass, and density stop behaving independently. At extreme scales, the familiar rules break. What emerges from this inversion is a single unsettling idea. Earth does not have a natural size. Its dimensions are a consequence of balance. Balance between gravity and electromagnetic forces. Balance between pressure and temperature. Balance between cosmic expansion and local attraction. Change those balances, and Earth either disperses into dust or collapses into something unrecognizable. Earth's existence as a planet is not guaranteed by matter itself. It is a transient arrangement within a universe that overwhelmingly favors emptiness. And yet, within this emptiness, complexity appears. Atoms assemble into molecules. Molecules form cells. Cells organize into organisms. Organisms develop awareness. From a universe that is mostly nothing, something capable of reflection emerges. This is the final inversion. The universe grows vast, then empty. Matter shrinks, then empties again. And between these two extremes lies a narrow window where structure becomes meaningful. Earth exists in that window, not because it is large or fundamental, but because it sits at a crossroads of scales. Large enough to sustain gravity, small enough to remain stable, complex enough to host life, simple enough to endure. The journey inward does not restore Earth's importance in any cosmic sense. It does something stranger. It shows that importance was never tied to size at all. It arises from organization, from balance, from the rare alignment of conditions that allow emptiness to briefly arrange itself into something that can look back at the universe and ask what it means. After shrinking Earth from planets to atoms, after watching solidity dissolve into emptiness, one final dimension remains to be confronted. Scale is not only a matter of size, it is also a matter of time. Earth may feel stable beneath our feet, but stability is a temporary illusion when measured against the age of the universe. Earth formed about 4.5 billion years ago, long after the universe itself came into existence. The universe is roughly 13.8 billion years old, meaning Earth arrived when nearly 2/3 of cosmic history had already passed. Stars had been born and died. Galaxies had merged and evolved. Heavy elements forged in ancient supernovae were already drifting through space before they ever became part of our planet. Earth was assembled from the remnants of earlier stars, a late product of processes that had been unfolding for billions of years before it existed. Even after Earth formed, it was not immediately a world capable of hosting life. For hundreds of millions of years, it was a molten, chaotic sphere, bombarded by debris, its surface constantly reshaped by impacts and volcanic activity. The earliest evidence of life appears around 3.8 billion years ago, but for most of Earth's history, life remained simple. Single-celled organisms dominated the planet for billions of years. Complex multicellular life did not emerge until roughly 600 million years ago. Dinosaurs appeared only about 230 million years ago and vanished 66 million years ago. All of recorded human history, every civilization, every war, every discovery, fits into the last few thousand years. In cosmic terms, humanity occupies the thinnest sliver imaginable. To make this imbalance clearer, scientists often compress the entire history of the universe into a single calendar year. In this cosmic calendar, the Big Bang occurs at midnight on January 1st. The Milky Way forms in March. The Sun and Earth do not appear until early September. The earliest life on Earth emerges around September 21st. Dinosaurs appear on December 24th and disappear on December 30th. Modern humans arrive late on December 31st, just minutes before midnight. All of human civilization, from the first cities to the present moment, unfolds in the final seconds of the year. Everything we care about occupies a fraction of cosmic time. And yet, the story does not end here. Earth itself has a future, and that future is finite. In about 1 billion years, the Sun's increasing brightness will likely render Earth uninhabitable, evaporating oceans and destabilizing the climate. In roughly 5 billion years, the Sun will exhaust the hydrogen in its core and expand into a red giant, engulfing or scorching the inner planets. Whether Earth is consumed or left as a barren remnant, its era as a living world will end. Far beyond that, the universe itself continues evolving. Star formation will slow as gas is depleted. Galaxies will drift apart as cosmic expansion accelerates. In trillions of years, most stars will fade into remnants. Black holes will eventually evaporate. The universe will grow darker, colder, and more diffuse. Against this timeline, Earth is not just small in space, it is fleeting in time. Its existence as a habitable planet occupies a narrow window between cosmic beginnings and cosmic endings. The same balance that gives Earth structure also limits its duration. This realization does not diminish Earth's significance. It reframes it. Earth matters not because it is ancient or enduring, but because it is brief. It exists during a rare moment when conditions allow complexity, memory, and awareness to arise. In a universe measured in billions and trillions of years, Earth is a short-lived phenomenon. And within that short span, conscious life has appeared just long enough to notice how temporary everything is. After confronting how small Earth is in space, how fragile it is in matter, and how brief it is in time, it is tempting to draw a bleak conclusion. If Earth is so tiny, so temporary, and so easily erased by cosmic forces, then perhaps it does not matter at all. This is the point where scale seems to drain meaning from existence. But this is also where a deeper understanding begins. Because meaning does not arise from size, duration, or cosmic dominance. It arises from perspective. Few people articulated this more clearly than Carl Sagan, who reflected on a photograph taken by the Voyager spacecraft as it looked back toward Earth from the outer reaches of the solar system. In that image, Earth appears as a single pale pixel, suspended in a beam of sunlight, barely distinguishable from background noise. To the camera, Earth was nothing special, just another point of light. But to us, that point contained everything. Every person who ever lived, every culture, language, and belief, every joy and every suffering, every hope, fear, invention, and mistake. The image did not diminish Earth. It exposed the mistake of equating physical prominence with importance. Earth's smallness does not make it meaningless. It makes it precious. From the perspective of the universe, Earth is insignificant. From the perspective of those who live on it, it is everything. There is no contradiction here. Meaning is not assigned by the universe. It is generated locally, by conscious beings capable of experience. The universe does not care whether Earth exists or not. But we do, and that difference changes everything. Earth is the only place we know where the universe has become aware of itself. Through life, through thought, through reflection, matter has organized itself into something capable of asking questions about its own origin and fate. That alone gives Earth a unique role, not because it is central, but because it is conscious. Smallness, in this context, becomes a responsibility rather than a dismissal. When you realize that every human conflict, every division, every claim of absolute truth unfolds on a planet smaller than a pixel in a vast cosmic expanse, the grounds for arrogance begin to collapse. Borders vanish. Hierarchies lose their justification. From far enough away, there are no nations, no ideologies, no chosen peoples. There is only a fragile sphere carrying life through an indifferent universe. This does not make human concerns trivial. It reframes them. It reminds us that cruelty is unnecessary, that hatred is parochial, and that cooperation is not idealism, but survival. Earth's fragility is not an abstract concept. It is a physical reality. The same forces that allowed life to emerge can erase it. Asteroid impacts, climate instability, nuclear weapons, ecological collapse. These are not cosmic inevitabilities. They are risks shaped by behavior. When Earth is understood as rare, temporary, and unprotected, the moral weight of human action increases. There is no backup planet waiting to receive us. No second Earth guaranteed elsewhere. Even if life exists in many places, even if Earth is not unique in the universe, it is unique to us. This is the only world we have ever known, the only one whose landscapes shaped our minds, the only one where our history unfolded. That fact alone carries responsibility. Smallness does not absolve us of consequence. It concentrates it. When Earth was believed to be the center of everything, responsibility could be deferred upward, to gods, to destiny, to cosmic order. But once Earth is understood as one fragile world among countless others, responsibility comes home. There is no higher authority managing outcomes. There is no cosmic safeguard ensuring fairness or continuity. What happens here depends on what happens here. That realization can feel heavy, but it can also be liberating. If meaning is not handed down by the universe, then it is something we create. Care, compassion, curiosity, and restraint are not mandated by cosmic law. They are choices made in full awareness of how rare and vulnerable this situation is. The universe does not require us to be kind, but the conditions that allow us to exist make kindness rational. They make preservation sensible. They make humility intelligent. The pale blue dot is not a symbol of insignificance. It is a symbol of focus. Everything that matters to us happens on that dot. Every future worth imagining depends on it remaining intact long enough for imagination to continue. In a universe that offers no inherent meaning, Earth becomes meaningful precisely because it is small, temporary, and alone. Not chosen, not protected, just briefly alive. And that fleeting existence is not a reason for despair. It is a reason for care. Once meaning is no longer anchored to size or centrality, the history of human knowledge takes on a new shape. Our understanding of the universe has never moved in a straight line toward comfort. Instead, it has repeatedly stripped away assumptions that once felt obvious and reassuring. For most of human history, Earth was not just home. It was the center of everything. The sky appeared to revolve around us. The sun rose and set for our benefit. The stars traced perfect circles overhead, reinforcing the idea that humanity occupied a privileged position in a carefully arranged cosmos. This geocentric view was not born from arrogance. It was born from experience. When every observation places you at the center, it takes extraordinary imagination to question that placement. The first cracks appeared when careful observers noticed inconsistencies. Planets wandered across the sky in ways that could not be neatly explained. Complex systems of epicycles were invented to preserve Earth's central role, mathematical contortions designed to save an assumption rather than test it. Eventually, a simpler idea emerged. Nicholas Copernicus proposed that Earth was not the center at all, but one planet among others, orbiting the Sun. This suggestion did not immediately overturn the old worldview. It was unsettling, counterintuitive, and dangerous. It removed humanity from the cosmic throne and replaced certainty with motion. Earth was no longer still. It was moving. That shift alone was enough to provoke resistance. Galileo Galilei took the next step, not through philosophy, but through observation. By turning a telescope toward the sky, he saw moons orbiting Jupiter, demonstrating that not everything revolved around Earth. He observed phases of Venus that could only be explained if it orbited the Sun. These discoveries were not abstract arguments. They were visual evidence, and they carried consequences. Galileo's insistence on following observation over doctrine challenged authority itself. The lesson was clear. Reality does not adjust to belief. Belief must adjust to reality. Earth's demotion was not merely astronomical, it was psychological. It forced humanity to accept that intuition is not a reliable guide to cosmic truth. Centuries later, another dethroning followed. For a long time, even after Earth lost its central place, the Milky Way was assumed to be the entire universe. It was imagined as a static, eternal structure, with the Sun somewhere near its middle. That illusion collapsed in the early 20th century when Edwin Hubble demonstrated that the faint spiral nebulae scattered across the sky were not clouds within our galaxy, but entire galaxies themselves, located millions of light years away. The universe suddenly exploded in scale. The Milky Way became one among countless others. And then came the most destabilizing discovery of all. Hubble found that the universe was expanding. Distant galaxies were moving away from us, and the farther they were, the faster they receded. This meant the universe had a beginning. It meant that space itself was dynamic, stretching, evolving. Earth was not located at a special center of expansion. Every point sees the same pattern. There is no cosmic middle. The dethroning was complete. Earth was not the center of the solar system. The Sun was not the center of the galaxy. The Milky Way was not the center of the universe. At each step, human importance receded, not because humans became less meaningful, but because the universe turned out to be far larger and stranger than imagined. This pattern repeats across disciplines. Biology displaced humanity from a special creation, revealing our kinship with all life. Geology revealed that Earth's history stretches far beyond human memory. Evolution showed that intelligence is not a predetermined outcome, but a contingent one. Each discovery reduced certainty and increased humility. None of this diminished human capacity. It sharpened it. Knowledge grows not by confirming what we wish were true, but by surviving contact with what is. Intellectual humility is not weakness. It is the engine of understanding. Every time humanity accepted a loss of centrality, it gained a deeper, more accurate picture of reality. The universe did not become colder or emptier because Earth moved from the center. It became more honest. And honesty, though unsettling, is fertile ground for wisdom. Our place in the cosmos is not defined by position, but by participation. We are not observers standing outside the universe. We are products of it, shaped by its laws, composed of its matter, animated by processes that began billions of years before Earth existed. Recognizing that lineage does not reduce us, it connects us. The history of human knowledge is not a story of humiliation. It is a story of maturation. Each time we let go of a comforting illusion, we gained a clearer view of where we truly are. And that clarity, hard-won and incomplete, is the foundation for everything that comes next. Once humanity accepted that it was not central, not chosen, and not guaranteed, a new question emerged naturally from that humility. If Earth is not special by position, could it still be special by outcome? In a universe containing trillions of galaxies and unimaginable numbers of planets, life should not be rare. The chemistry of life relies on common elements. Water is abundant. Organic molecules form easily in space. Modern astronomy has confirmed that planets are everywhere. Most stars host them. Many of those planets orbit within zones where liquid water could exist. By every statistical expectation, the universe should be teeming with life. And yet, when we look outward, we hear nothing. This contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked a simple question: where is everybody? If intelligent civilizations are common, if technology arises naturally from evolution, then the galaxy should show signs of activity. Signals, structures, probes, or at least unmistakable traces of engineering should be visible across cosmic distances. But the sky remains silent. No confirmed transmissions, no alien artifacts, no clear evidence that intelligence has spread beyond its homeworld anywhere we can see. This silence is unsettling because it forces us to confront possibilities that challenge our assumptions. One explanation is that intelligent life is extremely rare. While simple life may arise easily, the transition to complex, tool-using, technological intelligence could be extraordinarily difficult. On Earth, life appeared quickly, but for billions of years it remained microbial. Multicellular life emerged late. Intelligence capable of altering the planet appeared only very recently. It may be that Earth passed through a series of unlikely bottlenecks, each one filtering out most worlds. If that is true, then Earth is not just small, it is statistically unusual. Another possibility is that intelligent civilizations tend to destroy themselves before spreading far. Technology amplifies power faster than wisdom. Nuclear weapons, ecological collapse, uncontrolled artificial systems. These are not science fiction risks. They are real, and they arise naturally from intelligence without foresight. If civilizations routinely eliminate themselves shortly after achieving technological capability, the universe could be full of brief sparks that vanish before they ever meet. The silence would then be a warning, not an absence, a message written in emptiness. There are other explanations. Advanced civilizations might choose not to broadcast their presence, either out of caution or disinterest. They may communicate in ways we do not yet understand, using technologies beyond our detection. They may exist primarily in digital or non-biological forms, reducing their need for large-scale physical expansion. Or they may be separated from us by distances and times so vast that overlap is rare. A civilization could rise and fall millions of years before another appears nearby, missing each other entirely in the darkness. The universe may not be empty of intelligence. It may simply be asynchronous. But regardless of which explanation is correct, the implications converge on a single unsettling idea. Earth may carry a disproportionate share of responsibility. If intelligent life is rare, then preserving it matters more than ever. If intelligence tends to self-destruct, then survival becomes an ethical achievement, not a default outcome. If civilizations remain isolated, then what happens on Earth may never be corrected, balanced, or witnessed elsewhere. There is no cosmic audience, no external intervention, no guarantee of continuity. Earth's smallness, combined with the possibility of uniqueness, reframes intelligence itself. Intelligence is not merely a clever adaptation. It is a fragile condition. It creates the ability to shape environments, but also the ability to erase futures. It allows reflection, but also enables denial. In a universe that does not provide guidance, intelligence must supply its own. The silence of the cosmos is not comforting, but it is clarifying. It strips away the fantasy that someone else will carry the torch if we drop it. It forces us to consider that consciousness may be a rare phenomenon, emerging briefly in scattered places, vulnerable to extinction at every stage. Earth may not be the only place where intelligence has arisen, but it is the only place we know where it has. That alone gives our choices weight beyond local consequence. In earlier eras, humanity could imagine itself as part of a grand design, watched over by gods or destined for expansion. The modern view is harsher and more honest. There is no evidence that the universe cares whether intelligence persists. If it does, it is because intelligence chose to care about itself. Earth's potential uniqueness does not grant it cosmic authority. It grants it obligation. If this planet hosts one of the few places where the universe has become aware of itself, then the continuation of that awareness is not guaranteed by scale, destiny, or probability. It depends on restraint, cooperation, and long-term thinking. The paradox of silence transforms Earth's smallness into something else entirely. Not insignificance, but vulnerability. And from vulnerability arises responsibility. If Earth's potential uniqueness carries responsibility, then the future becomes more than a distant abstraction. It becomes a test. The universe does not promise continuity. It only provides conditions, and those conditions change. The future of Earth is shaped first by forces far beyond human control. The sun, which has quietly sustained life for billions of years, is not static. As it ages, it slowly grows brighter. In roughly 1 billion years, this gradual increase in energy will likely push Earth beyond the limits of habitability. Oceans may begin to evaporate. Carbon cycles may break down. Long before the sun reaches the dramatic red giant phase, Earth could become a barren world, stripped of surface water and incapable of supporting complex life. In about 5 billion years, the Sun will exhaust its core fuel and expand outward. Whether Earth is engulfed or merely scorched into lifeless rock, its role as a living planet will end. These outcomes are not threats to be avoided. They are the natural evolution of stars. Against such timescales, no civilization, no species, no technology can claim permanence. But between now and those distant endpoints lies a vast span of possibility. Earth remains habitable today, and it will remain so for many millions of years if destabilizing forces do not intervene. The question is not whether Earth has an expiration date. It is whether intelligence can extend its relevance beyond that date. This is where agency enters the picture. For the first time in Earth's history, a species exists that understands planetary limits and cosmic timelines. That understanding creates a choice. Humanity can treat Earth as expendable, extracting value until collapse, or it can treat it as irreplaceable, managing complexity with care. Long-term habitability is not guaranteed by physics alone. It depends on behavior. Climate stability, biodiversity, and ecological balance are not automatic features of a living planet. They are maintained by feedback systems that can be disrupted. Unlike asteroid impacts or stellar evolution, many of the most immediate existential risks are self-generated. Nuclear war, engineered pandemics, uncontrolled artificial systems, environmental collapse. These are not cosmic inevitabilities. They are outcomes of decisions made without long-term perspective. The vastness of the universe does not protect us from ourselves. It isolates us with our consequences. Faced with this, some look outward for solutions. Space colonization is often imagined as an escape, a way to spread risk across multiple worlds. In principle, this is possible. Mars, icy moons, artificial habitats. These ideas are not fantasy. They are engineering challenges, but they are also far more difficult than popular imagination suggests. Space is hostile. Radiation, low gravity, resource scarcity, and isolation impose severe constraints. No off-world colony can exist without continuous support for generations. Colonization does not replace Earth. It depends on it. At least for the foreseeable future, Earth remains the only place capable of sustaining complex life at scale. That does not mean expansion is meaningless. It means expansion is not a shortcut. If humanity does spread beyond Earth, it will do so slowly, carefully, and only if it learns restraint first. The same behaviors that would destroy Earth would destroy any other world even faster. The future of humanity, then, is not written in stars or encoded in destiny. It is written in time horizons. Short-term thinking favors growth without consequence. Long-term thinking favors stability, cooperation, and foresight. In a universe that does not intervene, intelligence becomes its own safeguard. This is the quiet power of agency. Not control over cosmic forces, but control over response. Earth's smallness does not eliminate choice. It intensifies it. Every generation inherits a planet shaped by the decisions of those before it. The future is not a single path, but a narrowing corridor, defined by accumulated effects. Somewhere far ahead, Earth will cease to be habitable. That fact does not render present efforts meaningless. It gives them context. A candle that will eventually go out is not worthless while it burns. It illuminates what lies nearby. It allows action, memory, and connection. The same is true of Earth. The universe does not care how long intelligence lasts, but intelligence can care how it uses the time it has. Agency in a vast universe is not about conquering space or defying entropy. It is about stewardship during a fleeting window of possibility. Earth does not need to last forever to matter. It needs to last long enough for awareness to grow wiser than the forces that threaten it. After traveling outward across impossible distances, inward through atoms and emptiness, and forward through deep time and uncertain futures, we arrive back where we began. Not at the center of the universe, but at home. Earth is tiny. That truth has not changed. It is a small planet orbiting an ordinary star in an unremarkable galaxy, drifting through a universe so vast that even galaxies fade into abstraction. Nothing we have learned restores Earth to a position of cosmic importance. And yet, something else has quietly taken its place. Earth is irreplaceable, not because the universe needs it, but because we do. Scale does not determine value. Size does not confer meaning. The universe is filled with emptiness on scales both immense and microscopic. But meaning arises in the rare places where complexity, memory, and awareness briefly take hold. Earth is one of those places. It is the only one we know. Every breath ever taken, every story ever told, every question ever asked happened here. Not because Earth was chosen, but because circumstances aligned just long enough for life to emerge and reflect. Home is not defined by dominance or permanence. It is defined by familiarity, vulnerability, and connection. Earth is where gravity feels right, where water flows as liquid, where light warms rather than burns. It is where minds evolved to wonder about stars they would never reach and times they would never see. From the perspective of the cosmos, Earth is negligible. From the perspective of experience, it is everything. These truths do not cancel each other out. They coexist. The universe does not diminish Earth by being vast. It frames it. It reveals how unlikely this fragile balance is, how narrow the window in which awareness can exist. In that light, Earth's smallness becomes a reason for care rather than despair. Nothing else will preserve it for us. Nothing else assigns it meaning. That task belongs to those who live here, briefly, passing the world forward through time. And perhaps that is enough. Perhaps meaning was never meant to be eternal or universal. Perhaps it was always meant to be local, temporary, and deeply personal. A quiet agreement between life and the moment it inhabits. As the universe continues expanding into darkness, as stars burn out and structures dissolve, the fact that something once looked up and tried to understand may be one of the rarest things of all. Earth does not need to be large to matter. It needs only to remain a place where awareness can rest, even briefly. And so, as this journey ends, there is no grand conclusion to draw, no final revelation to hold on to, only a gentle recognition. You're on a small planet, in a vast universe, living during a fleeting moment when complexity is possible. That does not make your existence insignificant. It makes it precious. Let the scale of things quiet the noise rather than amplify it. Let the immensity outside soften the weight within. The universe is vast, but for now, this is where you are, and for this brief moment in cosmic time, that is enough.